Hello everyone, my name is Shatabdi. Welcome to ExamRat. Okay, so in our previous classes we had discussed about refraction of light and also the image formation by convex lenses. Okay, so before we start today's topic, let us just have a quick revision of what we had studied in the previous class. Okay. So we had talked about how refraction is basically the bending of light when light falls from one medium to another, and when we talk about convex lenses here, it's biconvex lens. So there's a refraction that occurs like this, somewhat like this. So from rarer to denser, obviously speed decreases, and from denser to rarer, again speed of light increases. So this is sort of the bending, and if you extend the incident ray, you always get the lateral displacement. So now the lenses are made in such a way that their thickness is very reduced. So now what is the importance of this reduction of the thickness? It is that this bending will become very infinitesimally small, as a result of which this lateral displacement will be almost equal to 0. So you will think as if the mediums are rare only, like this and this and this medium, all three mediums are rare. When I say this, I mean to say is that light will appear to go unrefracted, like almost unrefracted. Okay, it will follow the same rules as it was following when we talked about mirrors. When we talked about spherical mirrors, I hope you remember it. And if you have missed out on our previous lessons, you can just go to our YouTube channel. They're all there, free of cost. So when we talked about mirrors, we talked about how reflection was happening. Okay. So anyway, you know that when light is going through one single medium, there will be it will travel through the same speed, right? Its speed won't decrease. The speed was decreasing or increasing because it was changing mediums. So when you basically reduce the thickness of the lens in such a way, you will basically feel as if light is traveling through the same medium, and therefore there is no bending of light. Okay. So why are we talking about this? Because when we draw ray diagrams, suppose when we talked about image formation by biconvex lens, it followed the same rules as that of concave mirrors, right? We found certain similarities between the two, like light reflecting, say this is focus, this is center of curvature, this is optical center. In the mirror we used to call the intersection or the midpoint of the spherical surface as the principal as the pole, and here it is the optical center. So anyway, so light that travels parallel to the principal axis, you know what will happen to it? It will fall on the focus, right? Let this be the focus. So it will fall on the focus here. And at the same time, we remembered how a ray of light passing through the optical center will pass undiminished. So what is happening here is that we can understand that refraction here is only happening once, right? So the lens is made in such a way that here, when refraction was happening twice, once and twice, and here it was the lens was made in such a way that it seemed as if there was no refraction. So this is an intermediate condition where it is said that the refraction is taking place about the midpoint of the lens, or the mid axis of the lens, and the refraction is happening only once. Like, we are considering only it happening once. Also, when it was experimented and proven that when the light ray was passing through the optical center, there was no refraction. It was passing undiminished or unrefracted or without bending. So that is how we were getting the images. I told you that biconvex lens and concave mirror, they have similar properties in the way that both are converging in nature. Like, they will converge the light rays. In the same way, concave mirrors and concave lenses, biconcave lenses and convex mirrors, they will be similar in properties, in the sense they will be diverging in nature. Okay, so when we talked about the image formation by convex lenses, again we realize that no matter where you are putting the object, like if this is the center of curvature, this is the focus, and this is the pole, even if you put it here or here or here, the image will always be formed between the focus and the pole. It will be diminished, obviously, it will be erect, virtual, and diminished. And where did we use this property? We used this property when we talked about rear view mirrors of cars, when the car has to see, where the driver sitting here has to see the cars coming from farther distances, in the sense that if this is the field of view, then all the cars coming from far ahead has to be captured in this small mirror. And how is it possible? It is only possible if its size is reduced. So that is where convex mirrors come into action. Okay. Then we talked about their magnification formula, we talked about mirror formula, we talked about sign convention. Similar things also exist for lenses. Okay. So now image formation by concave lenses. So in the same way that convex mirror had only one outcome rather, so the concave mirrors will also have only one outcome. So this is the optical center, although it's not accurate because I'm drawing with a pen tab, but you guys should always use rulers to make it accurate. So we know that since we're talking about lenses, it will always have two optical centers, two focus, and two center of curvatures. Now, while talking about biconvex mirrors, we talked about how they are, obviously all lenses are part of two spherical mirrors, right? One is this one is this one. So obviously for convex mirror, this is the first reflecting surface, so it will be named as F1 and C1, F2 and C2. So for concave lenses, obviously an understanding that the thing will be opposite, right? So since this is the first reflecting surface, so this is F1, C1, F2, C2. Okay. So again, the same thing, that no matter where you put the object, we will get virtual, erect and diminished image. Let's just, so parallel ray, it will obviously diverge because it's a diverging lens, and it will be traced back. Similarly, sorry, what's happening? Yeah, sorry. So since it's diverging, it will basically be somewhere extended like this. So just make it meet the focus, even though it's not looking like that in the diagram. But just parallel ray will obviously pass through the focus, so just make sure that you pass it through the focus. And the second one will obviously be through the optical center. So let's just do it here arbitrarily. So basically you'll get the image somewhere here. Just use another color. So yeah. So basically you'll get the image here. So obviously image will be in the dotted lines, but since I had to make it look visible, so I used the green color. So you got virtual because the apparent meeting of rays, you got erect, and you got diminished. So no matter where the object is, the image will always be formed between focus and optical center. Okay. So now sign convention. Again, it is similar as to that what we talked about when we talked about mirrors. The object is always placed to the left side of the lens. So this implies that the light from the object falls on the lens from the left hand side. Yes. All distances parallel to the principal axis are measured from the optical center. So here optical center is our parameter of measuring. So everything measured on the right of it is positive and on the left of it is negative, like we talked about. So if you put an image, if you put an object here, AB, the object distance we know it's called as U. So we are measuring the distance from the optical center. So like this, we are measuring the distance, right? So it will be minus U. Why? Because if this is the Cartesian system, and this is positive x, this is negative x. So we are following this, that if we go towards the left of the origin, then it is negative. So object distance will always be negative. Now image can be on either side, right? So image can be positive also, negative also. If here is the image, it is plus V. If the image were here, it would have been negative V. So yeah, and also again the height, how you measure it, distance is measured perpendicular to and above the principal axis are taken as positive. So if the image were formed like this, then it would have been minus h, and this one is plus h. So that is, it's similar as that of mirrors. Okay, so lens formula. We had said that for mirrors, the formula was 1 by v plus 1 by u equals to 1 by f. For lens, it's basically 1 by v minus 1 by u equals to 1 by f. So the derivation is not important. All you have to remember is this much, where v is the image distance, u is the object distance, and f is the focal length. Okay. Magnification. When we talked about mirrors, we knew that magnification is minus v by u, right? For lens, there is no negative sign, it is just v by u. You can always write it as h dash by h, and here also same, where h dash is image height, h is object height. So in sums where h dash and h are not given, you always know that this is the alternative formula, but don't remember the negative sign here. Also, one thing, that when we are writing formulas, we will put the negative and the positive side accordingly as given in the formula, but when we substitute it, we will always give the appropriate signs. Like if this is the lens, this is the object, and this is the image, then we know both are on the left side of the optical center, so both of their distances will be negative. So if this is 20 and this is 25, we have to put the sign of both, which is, here it's minus 25 by minus 20. If they get cut or not, that is different issue, but we have to give this the signs. Now what does this sign denote? Like whether the magnification has ultimately has a negative sign or not, that will depend on whether this object is erect or inverted. So that is why this negative sign is important in here, and here also ultimately what the result comes is different. Like even if one of them was minus 25 and this was just 20, then the answer would have been come in negative, and then we would have understood like whether it was the object was erect or inverted. Okay. Our last discussion for today is part of the lens, and then we'll be done with the lens portion of the refraction chapter. So what does it say? It says that the ability of the lens to converge or diverge light rays depends on its focal length. Okay. So now we talk about focal length in a little bit more detail. It basically says that a convex lens of short focal length bends the light rays through large angles. So it focuses them closer to the optical center. Since you know that convex lenses, biconvex lenses, or just convex lenses in general, they are a converging lens. So what it means is that more the focal length, more will be the convergence power. Right, the power of the lens to converge, or convergence power. Right? So the shorter the focal length, the more will be, sorry, this is the greater than less than sign. So the So the shorter the focal length, the more is the convergence power of the convex lens, or biconvex lens in this case. So what it is basically saying that the more you reduce the distance between F and O, the more the light will converge towards the optical center. Similarly, concave lens of very short focal length causes higher divergence than the one with the longer focal length. So the dependence is the same, only here shorter the focal length, more is the divergence power. The degree of convergence or divergence of light rays achieved by lens is in terms of its power. So how the extent or the degree to which you can bend the light rays, either converge them or diverge them, depends on the power of the lens. Like, that is the definition of the power. It is represented by letter P, and its unit is diopter or capital D. So the power of a lens is defined as the reciprocal of its focal length. So when we calculate power, we basically write as P equals to 1 by F. So the power of a convex lens is positive and that of the concave lens is negative. It is easy to understand that because for a convex lens, we are considering the focal length of its first lens, right? Like the first reflecting surface. And you know it is this side, like the first focus is on this side, right? So this is the measurement, right? So this is positive because it is on the right side of the optical center, and we know everything measured right side of the optical center is positive. Similarly, concave lens, since concave lens, so this is the, it will be the first focus will be here. So this distance is calculated, and we know that always optical center's left side calculation are done in negative. So for a concave lens, the power is always negative. Okay, so that will be all for today. We have discussed again refraction through lenses, but this time concave. We again went through the mirror formula and the magnification formula. Last but not the least, the power. So in the next class, we are going to be talking about some sums related to all the portions that we've covered. So that will be all. Thank you for watching.